Wow.
Thanks for bearing with us as we got the technology here up and running. The reason this is a little unusual, I don't give this presentation real often. This is a little different than most of the ones that I do, and it requires a little different setup than we normally have. But it's something that I think you probably haven't heard before, most of you. And it's very different than the kind of presentations you normally hear on creation versus evolution that deal with fossils and geology and genes and DNA, and that stuff's all fascinating. I love it. I wanted to give you a different take on things, but it is a little bit abstract, and so it's going to require you to really think tonight, okay? But it will blow your socks off. This is very cool stuff. And there's absolutely no secular or evolutionary explanation for what I'm going to show you tonight. I'm going to give you a little window into the mind of God. How's that for an opener, huh? All right, so let's get started with the secret code of creation. I do have to start by saying that when I was young, and my mom would prepare these wonderful meals, but sometimes she'd prepare something I didn't like very much, like broccoli, for example. And the rule was you had to eat everything on your plate, before you get up. And sometimes in moments of maturity, I would eat the broccoli first so that I could then enjoy the rest of the meal, right? So in that spirit, we're going to do the broccoli first. Okay, but stay with me. It's going to get cool, okay? Just stay with me. There is a secret code that the Lord has built into numbers. We don't think about God creating numbers. We think about Him creating mountains and rivers and people, but you see, God is also sovereign over the abstract world of thought as well. And He's sovereign over mathematics. That's His language. And I want to show you the secret code that He's built into it, and it's incredibly beautiful. You're just going to be blown away by this. It's amazing. To start out with our broccoli section here, we need to talk about sets. A set is just a collection of elements, in this case numbers, that have a certain property in common. It's very simple. So a group of numbers that have a certain property in common, and in most sets, some numbers are included and other numbers are excluded because they don't have that common property. And just as a few basic examples, it's getting stuck here, isn't it? There we go. So, let's see. Come on. Consider the set of even numbers. There we go. And so, those numbers belong to the set, and the other ones do not belong to the set. That's pretty easy. No problem there. And so that's a particular set. We could consider the set of negative numbers, and that's a different set, and so different numbers will belong to it. Yes, some numbers are included, some numbers are excluded. Now those sets are very easy because you can tell just by looking at the number if it belongs or not. You know if something's divisible by 2 or not, and you know if it's negative or not. It's got the minus sign in front of it. That's pretty easy. Some sets are a little more complicated, and you can't tell just by looking at the number whether it belongs or not. You're going to have to do a little bit of thinking first. And so we're going to spend our time talking about what's called the Mandlebrot set. The Mandlebrot set. And it's defined a little bit more complexly, but just like any other set, some numbers belong in it and other numbers are excluded. The Mandlebrot set is the set of all numbers, which we're going to call C, lowercase c, for which this other number, Z, remains small according to this formula. And I know this looks very complicated. It's not. I'll take you through it. So there's this little formula here, and Z is a number, and it starts as 0. And the N means that there's a sequence of Z's. There's Z1, Z2, Z3, Z4, Z5, and it's just a sequence of numbers, like 1, 5, 7, whatever. And if that sequence remains small, then this number we're checking, C, is part of the Mandlebrot set. On the other hand, if the sequence of Z gets very large, then C is not a member of the Mandlebrot set. Again, sounds complicated, so we'll do a couple of examples here. Is the number 1 part of the Mandlebrot set? So in this case, C is 1. And so we're going to plug that into our little formula. And Z always starts as 0. And so our first iteration here, come on. Bill Gates puts anti-creation software on these things. I'm telling you. There we go. It's got a virus on there or something. All right. So our first Z is 0. That's all. That's the rule. It starts as 0. And so we have 0 squared plus 1. 0 squared is 0 plus 1 is 1. That's pretty easy. And so that's the new value of Z, you see. And so we're going to put that 1 back in. Okay, that's the new value of Z. So now you have 1 squared, which is 1 times 1 is 1, plus 1 is 2. Okay, I told you this was easy. It's not hard, okay? 0, 1, 2. Now we're going to put the 2 back in. Yes, 2 squared is 4, plus 1 is 5. Okay, yeah, you got that. I'm going to put that back in. 5 squared is 25, plus 1 is 26. Going to put that back in. 26 squared is big. Okay, so you see what's happening with the sequence of Z? It's getting bigger and bigger and bigger. So is 1 part of the Mandlebrot set? No, because remember, Z has to stay small for C to be part of the Mandlebrot set. So C equals 1 is not a member of the Mandlebrot set. So we found that it does not belong, but it wasn't simple. You can't tell just by looking at it. You got to run it through that little formula. So let's do another one here. Come on, computer. Is the number 0 part of the Mandlebrot set? So this time C equals 0. We're going to put that in to our formula. So Z squared plus 0 is the new value of Z. So the first value is always 0. It starts as 0. So we're going to put 0 squared is 0 plus 0 is 0. Okay. And we'll put that back in. 0 squared plus 0 is 0. Okay. Put that back in. Yeah. So you see what happens there? It just gets you just get more and more zeros. And so does Z stay small? Yes, it does. And so is 0 part of the Mandlebrot set? Yes, you got it. Easy. Tedious, but easy. Okay, one more, because I know this gets old after a while, but let's try -1. Is -1 part of the Mandlebrot set? So now we have Z squared minus 1 is the new value of Z, and Z always starts as 0. So we'll put that in first, and we'll have 0 squared minus 1 is -1, yes. And so that's our new value of Z, and we put that back in. -1 squared is +1, minus 1 is 0. Okay, we put that back in. 0 squared minus 1 is -1. Okay, you see what's happening there? 0, -1, 0, -1, 0. So it doesn't center in on one number, but does Z remain small? Yep. So is -1 part of the Mandlebrot set? Yeah, you got it. Easy. There's one more complication, and then it gets really cool, okay? The Mandlebrot set also includes the so-called imaginary numbers. You remember these? These are when you take the square root of a negative. And I hate the fact that they're called imaginary because it makes it sound like they don't exist, like they're just made up. They do exist, okay? God made the imaginary numbers too. That's just a name. And to add insult to injury, the other numbers are called real. But that's just a name. That's just a name. An imaginary number is one that when you square it, you get a negative. And that's a little hard for us to comprehend, isn't it? Because if you think about it, positive numbers, when you square them, you get a positive number. Yes. Negative numbers, when you square them, you get a positive number. So imaginary numbers are not positive, they're not negative, and they're not 0, because when you square 0, you get 0, right? So how do you square a number and get a negative? That's a little hard. It's a little hard for us to imagine a number that's not positive, is not negative, and is not 0. But that's what imaginary numbers are. And that bothers people because it's counterintuitive. But intuition's based on experience. And when you're really little, negative numbers bother you. Because how can you have, you got 1 apple or 2, how can you have less than 0 apples? That doesn't make sense, right? And you get a little older, you get a bank account, suddenly negative numbers start making a lot of sense, right? I can have less than nothing, yes. It's the same way with the imaginary numbers. It's just that most adults never really gain experience with imaginary numbers, but they do exist. They do exist. And the way to think of them is, if you have the number line here, I'm sorry, my computer keeps burping, but there it is. The positive numbers are to the right of 0. The negative numbers are to the left of 0. Come on, computer. There we go. So where would you put the negative, or where would you put the imaginary numbers? Well, they're not 0, so one way to put it is off the number line. That's the way to think of it. They're on a different axis. They're not. See, the imaginary number there, I, is the most basic imaginary number. You square it and you get -1. And it's not positive. It's not to the right of 0. It's not negative. It's not to the left of 0. And it's not 0, because it's not where 0 is, you see. And so you can think of the numbers as being in a plane rather than a number line, a number plane. And you can multiply I by the real numbers and get any imaginary number. Half I, negative I, okay? And you see that you get this other axis there. And you can also have what they call complex numbers, and complex numbers have a real component and an imaginary component. And you can think of them as being off axis. you see. And so the x coordinate is given by the real component, and the y coordinate is given by the imaginary coordinate. But it's considered one number. And that's the neat thing about complex numbers, is you can map a position on a plane using simply one number, with the real component being its x coordinate and the imaginary number being its y coordinate. So that's a way to think about imaginary numbers. They're off axis. Now the Mandlebrot set also includes these imaginary numbers. I don't know why this thing is acting up, but it is. We checked the number 1, and we said it's not part of the Mandlebrot set. Maybe you run it through that formula, and z got big, so 1 is not part of the Mandlebrot set. I'm trying to see if there's a pattern, okay? We checked. Let me just escape here. I don't know why this is malfunctioning. Oh, it's not going to let me escape. Wow. There we go. There we go. We tried 0, and we found that it did belong, right? We tried -1, we found it did belong. I won't take you through the tediousness of trying these other ones, but had we tried -2, we would find it does belong. Z stays small. But -3 doesn't belong. Z gets big. A half, positive a half, Z gets big. But positive a fourth, as Z say, you can't tell just by looking at the numbers. There's no apparent pattern. And we could do the same thing with the imaginary number. We'd find it does belong. And so does -I, but 2i doesn't, and -2i doesn't, but a half I does, and negative. There's no pattern that I can see. And so perhaps what we could do then is we could plot it on a graph, right, with the real numbers representing the real component of the x-axis representing the real component, and the y-axis representing the imaginary component. And so all the numbers we checked, we'll color those black if they are part of the Mandlebrot set. So all the ones that are members, we'll plot those there. Those are the ones we checked, or could have checked, and they're black. And ones that are not part of the Mandlebrot set, we'll color those red. And so all these other ones, and they map there. Okay? And so maybe it'll form a shape, and then we can see if there's a pattern. And it turns out there is. And so as we plot more and more of these, a pattern starts to emerge. And it's not a pattern you'd expect. But you see a pattern starting to form there? The pattern that forms is this. Isn't that strange? Not simple. You'd think, well, maybe it'd be a circle or something. It turns out to be an incredibly complicated shape. All this is a map of which numbers belong to the Mandlebrot set. And so now you don't have to run them through that formula. What I did is I had the computer run through all possible points there, you see. And so you can see that 0 is part of the Mandlebrot set because it's black. You can see positive 1/4 is, positive half is not because it's red. And what I did was, if it's close to the Mandlebrot set, where Z does get big, but it does so very slowly, I colored them yellow, and that gives it a little bit of contrast. So yellow is where it's very close to being part of the Mandlebrot set, but still not quite part of it. And so the shape is incredibly interesting, and it has all kinds of interesting mathematical properties. You have the main shape over here, kind of a heart shape. They call that a cardioid. And that's where if you take remember those old spirographs that they used to have? If you take 2 gears of equal size and you put a pencil on one and roll it around the other one, that's the shape you'll get. That's a cardioid. And then all the other shapes are circles. Now it's a little squashed because of the aspect ratio of the screen, but those are absolutely perfect circles that are sort of growing off the cardioid. How about that? Into that sort of bug-like shaped thing. And it's got a spike on the end, and it's got another little shape over there. But it's really interesting. You got a circle here, and you got a circle growing on top of that one, and a circle growing on top of that one. You got a big circle here, and one growing off of it, one growing off of it, one growing off of it. Really fascinating. And now I'm going to remove the coordinates, because you can see that it's very mathematical. This circle is centered right on -1, just exactly. And it has a radius of, it looks like, what, about 1/4, something like that. So it's really an interesting shape. And totally unexpected. Yes, we did that. I don't know why this thing's acting up. Let's try this one more time here. Okay, so there's the coordinate with the coordinate system gone, so you can see the entire shape. And we're just going to spend some time exploring the shape, because the thing that I want to get across to you is this is not a shape that people made, right? This is a shape that is built into numbers. All this is a plot of which numbers belong to that Mandlebrot set. That's all it is. And it turns out to be wonderfully interesting. We're going to zoom in on sections of it here in just a second. The upper portion here, you can see that this top sphere branches off into 3 branches, right? A stem and 2 branches, so 3 total. That's kind of interesting. The one next to it branches off. I don't know if you can see that, but it branches off into 5 branches. Can you count that? Can you see that? The next one, they're getting small, but it branches off into 7. And the next one, 9, 11, 13, 15, all the way, all the odd numbers, all the way down to infinity. Odd infinity, apparently. Whatever that means. On the other side, you get all the numbers, including the evens and the odds. Interesting in terms of the way they branch. Isn't that fascinating? So it knows how to count somehow, which is wild. And perhaps even more interestingly, 5 plus 3 is 8, yes? Right? And the little shape in between them has 8. And that's always the case. Whenever you check the bud in between 2, it adds the number of stems, no matter which one, no matter where you're at. So again, 3 and 4 is 7. That's how many it has. 4 and 5 is 9. That's how many it has, and so on. So somehow it knows how to add. That's kind of neat. Just amazing. Incredible shape. Okay, we're going to spend some time exploring this. And one thing I want to check out is this little that spike there on the end. You see that spike? Because it's got a little black spot on it. What could that be? Well, let's find out. We're going to zoom in on that little thing. Oh. Isn't that interesting? It's a baby version, right? It's the same basic shape as the parent. It's got the cardioid, and you got the little circles growing off of it. It's not identical. It's very similar, but it's not identical. It has extra spikes growing off of it. The parent didn't have these. They're very faint, but the parent didn't have these extra spikes growing off of it. So it is, and it's got a baby. Oh yeah, how about that? And on the, of course, on the tail of that is another one. Let's see if I can go to that one. How about that? And you could do that forever, literally. Yeah. There it is. And every time you get, we zoomed in on a spike, and the baby version has more and more spikes as you zoom in. So it inherits the property of the section of the parent that it grows off of, apparently. So all that on a tiny little section of a tiny little section of a tiny little section of the Mandlebrot set. And if you're wondering, there's nothing bigger. That's the ultimate one right there. There's nothing outside of it, interestingly. Other places we can go exploring. They call this the Valley of the Seahorses. Can you see the seahorses? By the way, the colors are arbitrary. We can make those whatever we like. But the shape is something that God has built into numbers. That's what you need to keep in mind. This is not a human artist that made this. The computer helped us plot it, but the shape is built into numbers. This is just the shape you get when you plot what points belong to the Mandlebrot set. See the seahorses over there on the right side? They're upside down, and they're a little dark on the screen, but they really do look like seahorses. It's kind of amazing. So let's go off to the right here. We'll zoom in a bit on one of these seahorses. Now again, all you're looking at is a plot of which points belong to the Mandlebrot set, and it turns out to be wonderfully complex and beautiful. Isn't that amazing? God has built this shape into numbers, hidden there for nearly 6,000 years, and human beings discovered this in the 1970s, and actually 1980s. How about that? It was waiting there for us, but there it is, built into not the physical world, but into the abstract world of mathematics. Amazing. And I should point out too, remember the points that are very bright are points that are very close to being on the Mandlebrot set, but aren't quite on it. And so that tells you everywhere you see one of these bright points, it's actually close to a black spot that's actually part of the Mandlebrot set. It just gets so thin you can't see the black anymore. It's like a thin wire that wiggles around. It's just incredibly wiggly, you see. And in fact, mathematically, it's as wiggly as it can possibly be in 2 dimensions, if that means anything to you. Which it really doesn't to me, but anyway. Now, I found from experience, you can zoom in on the center of that till your heart's content and nothing really changes. It just keeps going forever. Little window into the mind of God. Because that's how God thinks about things. He's infinite. And this gives us a little taste of that, doesn't it? Just a little taste of it. So I thought, well, let's go off axis then. Let's see what these threads are made of. And we have this beautiful spiderweb type structure. And I want to see what the threads of the spiderweb are made of. Yes? So let's zoom in to one of those. And they're made of more spiderwebs, smaller spiderwebs. How about that? And here you have you got the central hub of that spider web, and you got another one up there, and they intersect in the middle. And there's a little black spot there. Let's zoom in on that a bit. Oh, how about that? Isn't that interesting? You got a feeling like God really likes that shape or something? It's built into math, built into numbers. And again, it's not identical to the parent. The main shape is, but it's got extra stuff growing off of it. We zoomed into a spider web, and it's got extra spider webs growing all the way around it, you see. And you might notice it's got a little baby version too. It gets computer intensive to zoom in too much though, so we'll go back out here. But all of that's in a tiny little section of the Mandlebrot set. That's what it is. Isn't that phenomenal? Well, let's explore. Let's go back to that valley. We went off to the right last time. Let's go to the left this time. They call that the Valley of the Double Spirals. And so you see those shapes there. As we zoom in a bit, it'll be easier to see. They're double spirals, and by double spiral, I mean it's got two strands that interleave together. If you follow this strand around right here, it goes around like that, and comes in, and is right here. There's one in between, see? This strand and this strand are the same. This strand and this strand are the same. So it's two strands wrapped around each other, a double spiral. And again, I found you can zoom into the middle of that forever, and it just keeps going. It's infinite. And so let's go off axis and look at one of these strands to see what they're made of. And they're made up of, well, spider webs and more of these double spirals. And we have a new structure in the middle. I call them a bow tie. Doesn't it look like a bow tie right there? Kind of. So let's zoom in on that bow tie a little bit. And it's made up of two double spirals, and they intersect in the middle. And then 2 becomes 4. You see 4 in the middle. It's kind of a cross structure. That's kind of pretty. And then 4 goes to 8. Oh, you were expecting it this time, weren't you? Yeah. How about that? Once again, you got the baby version of the Mandlebrot set built into itself. Phenomenal. And think about it. It's got you can see the little spike there. It's got a baby version of that. You could zoom in onto that. You could zoom in on the Valley of the Seahorses on that one. And it would just keep going forever. It has an infinite number of babies built into each baby. It's remarkable. And incredibly beautiful. I get to pick the colors, but the shape is God's. Yeah. Well, I wanted to see what else this thing has to offer, so let's zoom in on some other sections. Let's zoom in over here on this cardioid shape, and this they call the Valley of the Elephants. Mathematicians like to make up fun names for these things, but it really does look like elephants, doesn't it? See the elephants marching along in formation, the trunk there, and it's all curled up? So isn't that interesting? We'll zoom in on the trunk here of this elephant, and this is a single spiral, not a double spiral, so it's just one strand. And let's zoom in on the threads of that. And again, you can zoom in, any spiral you zoom in on, you can zoom in on it forever. And it'll continue. We got now spider web type structures. We got single spirals, and now we have bow ties again, but now the bow ties are made up of single spirals. So it's interesting. Whatever part you zoom in on, it kind of inherits the properties that you're zooming in on there. Is that not stunning? It goes from 2, and then in the middle there, you can see 4, and 8, and 16, and 32, and 64. See? And once again, you got a baby version built into it, so you can't escape that, apparently. Just remarkable. And just to think about what we're looking at. I mean, it's one thing to say, well, that's very pretty, but it's another thing to think about what you're seeing. You're seeing a map that God has built into numbers. That's what we're seeing. A little window into how God thinks about numbers. That's what it is. That's why it's beautiful. It comes from God. There's no secular explanation for this. I'll talk more about that later on, but there's something to process. There is no secular explanation for this. Let's zoom over here on this valley. This is the one valley over, and they call this the Valley of the Scepters because it looks very similar to Seahorse Valley, right? You got seahorses over on the right and double spirals on the left, but now they have scepters growing off of their foreheads. You see, they're sea unicorns now. And so I thought, well, let's zoom in on one of those guys. And since we haven't seen a scepter before, I thought that might be fun to zoom in on. It's just fun to go exploring in this shape, and it's something. It's an aspect of creation that we've only been able to explore in the last 30 years or so. Because even though it's been built into math from all eternity by God, it's only something that we've had computing power to be able to explore recently. You could theoretically plot this by hand, but it would take forever. Okay? So you can zoom in, there's a cross structure in the middle, and again it goes from 4 to 8 to 16 and 32 and 64 and all the way into another baby Mandlebrot. Anywhere you see intersecting structures, I've sort of learned where to look to find them now, but anywhere you see intersecting structures, you'll get a baby Mandlebrot right in the middle of them. Incredibly beautiful. Now that is all just a map of what numbers belong to that formula. That when you plug the numbers in, they stay small, z stays small. That's it. It's that simple. And that made me think, what happens if you change the formula? So I thought I'll try that. What happens if we make it z cubed plus c? I find if you change c, half c or whatever, it just changes the scale of it. It doesn't really change it very much. But if you make z cubed you get a different shape. You get that. Instead, a little different. And so everything kind of gets duplicated. The only thing that stays the same is this valley right here. That stays about the same. Everything else gets moved around. This bubble right here has split into two and moved up to here. So there's two tails now. You see, everything gets kind of doubled, or in some cases quadrupled. So this little baby version right here, it gets split into four. So it's there, and there, and there. And later on I haven't incorporated this in the presentation, but later on I learned how to do it in stages. So z to the power of 2.1, 2.2, and you can actually watch it morph from one shape to the other. It's kind of interesting. But let's explore this new shape, which is sometimes called a Mandlebrot. So Mandlebrot is the original shape, and a Multibrot because it's a multiple of the Mandlebrot. And does it have similar properties? Well, let's find out. Let's zoom into what used to be the Valley of the Elephants, because that's the one place that didn't seem to change very much. You think we'll still have elephants? Well, let's find out. Yeah, you still got elephants. That's good. But now instead of having one elephant per bubble, you have two per bubble. You see, everything gets duplicated because the power went up one. So it's really interesting to look at how the math changes as you zoom in on these different shapes. Yes, there we go. So zooming in on the trunk of one of these elephants. And again, we have a single spiral. I think we'll have bow tie structures like we did before. Similar, but now there's three instead of two. See, it gains by one. And the next one in, you remember it went from 2 to 4 to 8 and so on. Now it goes from 3 to 9 to 27. It's all the powers of 3 as you zoom in. The next, see the number of bumps around that and so on. And look what you have in the middle there. It's a baby version of that shape then. So it repeats itself forever as well. This type of structure that repeats infinitely on smaller and smaller scales is called a fractal. And this is one type of fractal. There are other types of fractals as well, but I find these to be really interesting. I'm going to switch over to, yes. Now back to familiar PowerPoint. Okay. So z squared plus c gave us that shape. Z cubed plus c gave us that shape where everything gets kind of increased by 1. Let's try z to the 4th, see what that does. It's fun to explore these different shapes. Oh, you get kind of a threefold structure. Is there a pattern? You seen the pattern? Z cubed gave us kind of a double, twofold structure. Z to the 4th gave us a threefold structure. Apparently the number of lumps there is the power minus 1. So it occurred to me if I made z to the 7th, I could get snowflakes. And it works. You do get snowflakes. How about that? And when you zoom in on the snowflakes, I'm not going to do the whole thing, but you get the same type of patterns. You get these beautiful spirals, and you zoom in long enough and you get more snowflakes. The same shape repeats itself infinitely. And that is the nature of a fractal. And a fractal doesn't have to repeat exactly. It can repeat approximately. And there's different types of fractals. For example, there's a Sierpinski triangle. This is where you take a triangle, and this is one you can do yourself. You can take a triangle, and from the middle of it, you cut out a triangle 1/3 the size of the original. Now you have 3 triangles. You do the same thing with each of those. You cut out one triangle in the middle, 1/3 the size. Now you have 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles, and you cut out one from that, and so on and so forth. You do this forever, and you'll end up with a Sierpinski triangle. And you can see that any section of it sort of looks like the original, doesn't it? I could zoom in on this, and you can't really tell how much I'm zoomed in. That's the nature of a fractal. When you can't tell what the scale is by looking at it, that's a fractal. Or a Koch snowflake. And this is where you add on a triangle. You start with a triangle, and you add on a triangle to each side, and then you add on a triangle to each remaining side, and so on. And it gets more and more complicated. And you do it an infinite number of times, and you end up with this snowflake. And it's a very interesting shape mathematically. Mathematicians love to play with these sorts of things because it has finite area. You can see it's only so big, but the perimeter is infinite. Okay, because it's infinitely wiggly, and so an ant could never possibly walk all the way around it, even though it has finite area. Or another way to think of it is if I could make a paint can that has the shape, instead of it being a circle, it has that shape instead, but it just extended out one dimension. That paint can would have a finite volume, but an infinite surface area, which means it could only hold so much paint, but it couldn't possibly hold enough paint to paint itself, which is just, that's mind-blowing to me. But, I don't know, crazy. God isn't limited by our imagination. What does all this mean? I mean, we got these incredible shapes built into numbers, built into math. What conclusions can we draw from this? What causes the beauty that we see in these fractals? What causes the complexity that we see? The fact that they have these mathematical properties. What causes that? What causes the beauty in fractals? Is it the man-made color scheme? I picked the colors. I think they're pretty. But fractals are still pretty even in black and white, you see. So it's not that the shape is God's, and the shape is beautiful. Even if it's grayscale, it's still beautiful. So it's not the man-made color scheme. Although some people pick very bad color schemes, and shame on them. Did the computer create the beauty? Did the computer create these shapes? No, it revealed them to us. But these shapes are built into numbers. The computer just helps us plot it quickly. Like I said, you could, in principle, you could map one of these out. In fact, the Mandlebrot set, the main iterations of it have been done manually. Mathematicians love that sort of thing. I don't. It's interesting, but I'd rather let the computer do it. The computer didn't create it. The computer is like a microscope. A microscope does not create bacteria. It allows you to see bacteria. The computer allows us to see these fractals. Did people make it? Well, I mean, nobody knew about these until really the 1980s is when they were starting to, at IBM, they were looking at these things, and people were surprised by what they found. There's no way people could we can't make something infinitely complicated anyway. It's not like somebody sat down and said, I'm going to make a heart-shaped structure over here, and I'm going to put a bubble there, and an infinite number of bubbles, and no human being designed this shape. We discovered it, but we didn't create it. And the fact that we're surprised by its properties is proof that we didn't make it, right? You make something, you design it, you know how it works. We discovered this, but we didn't make it. The beauty appears to be built into math. It's built into math. What causes the complexity in fractals? The fact that they have infinite complexity to them. Did the computer do that? No, a computer is not infinitely complex. In fact, most programs that will graph fractals can only zoom in so far, and then the computer crashes because it can't deal with the high precision numbers. You have to write special code to go in deeper than that. The program that I wrote for this will only zoom in a few billion times, and then it says, I give up. But the fractal goes on. It's beyond what the computer can plot. Yes, so the computer didn't create it. Did human beings create it? Again, we didn't sit down and design this, so we can't design things that are infinitely complex. Machines that human beings make get simpler when you zoom in. These things get more complicated. They get more complex as you zoom in. That's not a property of a human-made object. Did the formula create it? Z squared plus C. I mean, we did pick the formula, but what we found is it doesn't matter too much what formula you pick. There's built-in complexity to the numbers. Remember, we changed the formula, and you still get these beautiful, incredible shapes. So the formula didn't create it. The formula reveals a particular beauty built into those numbers, but it didn't create it. The complexity seems to be built into numbers, built into math. By whom? Well, what is math? Mathematics is the study of the relationship between numbers. That's just the dictionary definition of it. It's the study of the relationship, how numbers relate to each other. Well, what are numbers? That sounds like a dummy question, doesn't it? But we all sort of know what numbers is, but define one. Yeah, it's kind of hard. And I looked through several different dictionaries, and most of them, they don't agree on what a number is. It's hard to define. Sometimes these things that are very simple, very basic to us, are the hardest to define. The best I could find is numbers are a concept of quantity. I think that's probably the best definition that is out there. Numbers are a concept of quantity. So when you're thinking in terms of the number, you have a quantity of objects. The number is the concept of that quantity. It's not the objects. It's the concept of the quantity of objects that you have there. And so the number is abstract. Numbers are concepts. They're abstract in nature, not physical, right? They exist in the mind. They're concepts. That's where concepts exist. You can't stub your toe on a number or pull one out of the refrigerator. They're not made up of atoms. They're abstract. Now you say, well, you can't literally see a number, and people might say, well, I see the number 3 right there. But that's not really the number 3, because if it is, I've just destroyed the number 3. Children will have to count 1, 2, 4, and so on. 3 is gone. That was a representation of the number 3. That was a numeral. Written numerals are not numbers. They're representations of numbers, okay? Writing down 3 doesn't mean that is literally 3. It's a symbol. It represents 3. Just like a picture of a horse symbolizes a horse, but it's not the horse. Laws of math are conceptual, okay? Concepts exist in the mind. Well, where did laws of math come from? Did they evolve? Now, this is interesting because, of course, my secular colleagues, they want to suck the creative juice from God out of everything, right? All these wonderful things in the physical world that God has made, they want to say, well, mutations and natural selection produced that organism. laws of math can't evolve because they don't change. I don't know any secularists that believe that the number 7 evolved from the number 3. 7's always been 7, 3's always been 3. And so you cannot explain math by evolution. You might find evolutionary biologists, evolutionary geologists, evolutionary astronomers. When it comes to math, everyone's a creationist. Isn't that interesting? You won't find any evolutionary mathematicians. They don't exist. You might find evolutionists who use math and so on, but they don't believe that math evolved. Were laws of math created by people? Well, laws of math are formulated by people. We invented the notation, that's why 3 looks like that. But we didn't create numbers. Numbers existed before people did. And laws of math existed before people did. As one example, the planets, the way they orbit the sun, they follow a particular law. They follow Kepler's laws. But Kepler didn't make those laws. He discovered them. And the planets orbited perfectly well before human beings were created. Right? 2 days before human beings were created. But anyway, they orbited perfectly fine. So the formulas existed before people discovered them. I mean, triangles still added up to, the sum of the squares of the 2 sides before Pythagoras discovered that. He didn't create triangles. Laws of math are not created by people. They didn't evolve. Do they come from the universe? Now, this is a common one. People say, well, that's a property of the universe. But I don't think you can make that argument. For one thing, the universe is constantly changing. It's expanding and stars explode and things like that. If laws of math were based on the universe, we'd expect them to be changing too. But they don't. So laws of math don't reflect the universe. Now, there is a relationship between the universe and laws of math. We'll get into that a little bit later. But you can't say they're created from the universe. In fact, 2 + 2 would equal 4 even if there were no universe. It's a transcendental truth, isn't it? It goes beyond nature. I'm going to say that laws of math stem from the mind of God. That's the only explanation that makes sense. Math is God's way of thinking about quantities. And that makes sense. That makes sense of the properties of laws of mathematics. Because if you think about it, laws of mathematics are conceptual, universal, invariant, exceptionless entities. Let's go through one each at a time. Conceptual, they exist in the mind. They're abstract. You can't touch a law of mathematics, okay? You can't literally see one. You can write down a representation of one, but they're not physical. They're conceptual. They exist in a mind. They're universal, meaning laws of mathematics apply everywhere. Doesn't matter where you go. 2 + 2 still equals 4 in Europe, okay? They're invariant. They don't change with time. It's not like, well, the Pythagorean theorem works on Tuesdays, sure, but everything's out on Fridays. Who knows? And they're exceptionless, right? It's not like, well, 2 + 2 normally equals 4, but in this case, it didn't. Right? Try to explain the bank error that way and see if they buy that. The reason you're missing millions of dollars, well, it just didn't add this time. I don't think they'd buy that. They're exceptionless. And these things make sense in light of the fact that laws of mathematics stem from the mind of God, because God's thoughts are conceptual, because all thoughts are conceptual. God is omnipresent, and so naturally his thoughts would be sovereign over the entire universe. So laws of math are going to be the same everywhere because God's the same everywhere. God does not change with time because he's beyond time, and therefore his thoughts will not change with time. So laws of mathematics don't change with time. And God is sovereign over everything, and so that's why laws of mathematics are exceptionless. And so if you think about it, the existence and properties of laws of mathematics and properties of numbers make sense in terms of the Christian worldview. But the naturalist has a problem. The person who says, well, there's no God, everything's evolved by chance. He's got a huge problem because on the one hand, he knows laws of mathematics are conceptual. They exist in a mind. We know that. They're not something you can stub your toe on. They're not physical. They're mental constructs. But they weren't created by human minds because they were around before human beings were around. And see, even secularists will acknowledge that. Of course, the planets orbited the sun perfectly fine before people. That law still worked. But they've got a problem because they don't believe in minds before human minds. See, the Christian, we have an answer to that. We can say there is a mind before human minds, and that mind is the mind of God. And so we can have laws, we can have conceptual laws before people in the Christian worldview, but the naturalist can't have that. They cannot make sense of laws of mathematics in their worldview. They accept them and move on and dismiss the inconsistency. Now here's another interesting tidbit. Physical fractals. We've looked at abstract fractals, right? That exist only on computer screens after we map them. But their true fractals repeat infinitely and are only found in the conceptual world of mathematics. We can represent them with physical plots, but they only exist actually in the mind of God ultimately. But the physical world also contains many things which are approximate fractals. They don't repeat forever, but they repeat many times. And so let's take a look at some examples of these. Snowflakes. have a fractal quality to them, because it's not that they repeat exactly, but they have the same basic type of shape, that six-fold shape, no matter how much you zoom in on them. So they repeat approximately, these little gems from heaven that God sends us every winter, and they're just stunningly beautiful, and they do have that fractal property to them, the six-fold shape being determined by the oxygen molecule and so on. And that stuff that forms on your windows, yeah, that's a fractal too, because it tends to repeat on smaller and smaller patterns. You can't tell immediately by looking at it how big the scale is. It's scale invariant, and quite lovely, really. I was always amazed by this when I was a child looking at the window. I'm still amazed by it. Look at the window and you see these beautiful patterns that form on there. They're fractal. Ferns have a fractal pattern to them. The overall fern is the same basic shape as a leaf, as a leaflet of a leaflet, and so on. It's the same basic shape. It repeats itself. I even found fractal broccoli, so broccoli is good for something after all. You see how it repeats it? Let me zoom in a little bit. You see, you got a cone, and it's made up of littler cones, which are made up of literal cones. And isn't that interesting? Wild. Coastlines have a fractal type shape. Now, these are the ones that don't repeat exactly, but they branch, and they branch into smaller branches and smaller branches and so on. And so that has a fractal property. The way mountain chains look is fractal often. The way they branch. Clouds are often fractal. You can't tell, am I zoomed in on a really small section of a cloud, or am I looking over at most of the sky? You can't tell because the same basic pattern repeats at smaller and smaller scales. The way lightning fragments is fractal. Is this lightning, or is it just a little spark? Well, in this case, you can tell only because there are buildings in the background. But if I did the same experiment with a little spark, it would branch the same way, pretty much. You can't really tell. And so the way lightning branches is in a fractal pattern. Isn't that spectacular? And it's even cooler to watch it in slow motion. You can actually watch it branching out into that fractal pattern. Really quite stunning and amazing. There it goes. Branching out and branching into branches and branching into branches of branches until one of the leaders hits, and then most of the current goes down that leader. So here's my question then. Why do fractals occur both in math, which is abstract, not made up of atoms, and the physical world, which is physical and is made up of atoms? Why do we have fractals in both? Same designer, yeah. That'll make sense of it, wouldn't it? So here we have a fractal that only exists in the abstract world of mathematics. You can't find that anywhere in the physical universe. But that one you can. They're very similar. Now this one, that's part of the Mandlebrot set. That exists nowhere in physical reality. But that one does. Isn't that interesting? This shape right here, it's called a Barnsley fern. You're probably thinking that's a real shape. It isn't. That's a mathematical graph. Yeah. And the entire shape, each of these leaflets is the same as the entire shape. And I'll prove that to you. Watch the entire shape here. It goes down and becomes one of its own leaflets. You see that? Yeah. Let me do that one more time just because it's cool. Isn't that neat? So each one, it repeats itself infinitely. So that exists nowhere in the physical universe, but that does. Isn't that interesting? That shape, built up into math. It doesn't exist anywhere physically, but that exists on your windows in the winter. That particular shape is a mathematical graph. It does not exist in physical reality, and this, unfortunately, does. This is part of the Mandlebrot set. It's one of those double spirals that we zoomed in on earlier. It exists nowhere in the physical universe, but that I've seen with a telescope. Isn't that interesting? You got fractals occurring in abstract and also made up of atoms. Why is that? And of course, the answer I'm going to lean toward is because God's mind is sovereign over the entire universe. Now, one answer that people might give would be, well, the physical universe obeys mathematical laws, right? So if something can occur in math, it stands to reason it can occur in the physical world because the physical world obeys math. And that's true, but it just pushes the question back, because now I'm going to ask, why does the physical world obey math? That's what I want to know. Why does the physical universe obey math? Well, in the Christian worldview, I can make sense of that. Mathematics are a reflection of God's thoughts, and the universe is upheld by the mind of God. So naturally, we'll see mathematical patterns in nature. It stands to reason in the Christian worldview. God upholds all things by the word of his power, and in him all things consist or hold together. Since God thinks mathematically about things, naturally the universe will be upheld in a mathematical way. But the secular worldview cannot answer that. Try it sometime. Ask an evolutionist, why does the physical universe obey mathematical laws? Now, they take it for granted. We all know it does. But why? You can't make sense of that in the secular worldview. The secular worldview cannot make sense of the properties of laws of mathematics, the fact that they're conceptual and yet existed before human minds, the fact that they're universal, apparently, we assume they're the same everywhere, that they're invariant, they don't change with time, that they're exceptionless, We can make sense of those properties. That's consistent with the mind of God. And the secularists cannot explain why the physical universe is compelled to obey mathematics. But we can, because God is sovereign over the physical universe. It makes sense in the Christian worldview. Don't believe me that secularists can't explain this? We have a physicist here, Eugene Wigner, bright guy, and he wrote a wonderful article that I would encourage you to read called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The unreasonable effectiveness of mathematics in the natural sciences. He's trying to explore, apparently from a secular perspective, why it is that the universe obeys math. And what is his answer? It's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. It's amazing enough, he says, that the universe obeys these wonderful laws of nature, and it's even more amazing that they happen to be in nice, neat mathematical equations like E equals mc squared that the human mind can understand. It's remarkable. And his conclusion in the article is, the miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. He doesn't have an answer in his worldview. Isn't that interesting? He's a bright guy. He's a physicist. The secularists have no explanation for that. Isn't that interesting? They can come up with evolutionary stories for fossils and genes and so on, but they've never come up with an evolutionary story for math because math can't evolve. It's there, and it's a problem for their worldview. They need it to survive. They have to live in God's universe, even though they might deny God. But they don't have any explanation for it in their own worldview. So we've seen there's a secret code of amazing beauty and complexity built into numbers. That's what I want you to take away. Numbers have incredible beauty and complexity built into them. Maps of certain very simply defined sets, like z squared plus c, show infinite complexity and tremendous beauty when you map them on that plane. Human beings did not create the complexity in fractals. We merely discovered it. It was there all along. Computers did not create the complexity in fractals. They merely helped plot it. You could, in principle, do this all manually. It would take forever, but you could. The intricacy of fractals is built into mathematics by God. That's the only explanation that makes sense. Fractals have no reasonable explanation in a secular or evolutionary worldview. You just can't make sense of them in that worldview. So, well, I hope you've enjoyed that. I know it was a little abstract, but I hope that it's something that you maybe haven't seen before and gives you a little more appreciation of the mind of God. We serve an awesome God. So thank you very much for having me out to speak.